Okay, so welcome to part 2 of Units. Let's get into it. So we've been talking about linear displacement. Today we need to talk about angular displacement. So angular displacement is basically just the angle that is made. For example, right here we have an angle, right? So usually we use theta. So theta is usually what we use to define an angle. But there are many different ways of defining angles, but the one that we usually like to use is degrees, right? So we know that one circle has got 360 degrees. I could also say one rotation equals 360 degrees. Another thing that you like to see is rotations. Okay, a rotation is actually an angular displacement. It's one full rotation is an angle, so 360 degrees. The last one that you'll probably run into at some point or another is a radian. Okay, a lot of people get confused by radians, but there are 2 pi radians in one rotation. Those 2 pi radians. Okay, in one rotation. So what is actually a radian? A radian is actually really cool, because if you take the radius of some circle and you lay it around, lay it around the circle, so that arc that subtends the angle here, and you draw this angle, okay, so you have an angle here. Take that radius, we make an angle out of it. That makes some angle here, right? That angle is 1 radian. And it works because even if you make the circle bigger, the radius is going to increase, but so will the arc that subtends. So in the end, the radian stays the same regardless of the radius. The angle of a radian stays the same. If you want to do a quick little conversion between rotations, we already got rotation as 2 pi radians. But the other conversion that you might need to do is 57.29 degrees equals 1 radian. So there's your conversions. I doubt that that you need to do those conversions, but too often. But we are going to do that in this class. We are going to do some conversions in this class, but in industry, you may not have to do those conversions too often. We don't really need that one. So, how do we measure angles? There's 2 main ways that I would measure an angle. One is using a protractor or a digital protractor, like what we have here, and the other is just to use some trigonometry. Okay. So, what is trigonometry? Well. If you haven't had trig yet, we're going to get into a little bit of trig. Not a lot, just a tiny bit. And I doubt that I even put this on your exam, but I did want to touch on it so that maybe you'll be better prepared for trig when you get to it. So something you probably, if you haven't remembered or don't remember from high school, but you do need to remember it, is SOHCAHTOA. SOHCAHTOA, right? So SOH is sine equals sine of some angle, so that's theta. We'll use theta there. Is opposite over hypotenuse. So opposite over adjacent hypotenuse. Okay, so it'll be the sine of some angle is equal to opposite side, the length of the opposite side divided by the length of the hypotenuse. You also have cosine, which is the adjacent side divided by hypotenuse. The length of the adjacent side divided by the length of the hypotenuse. And you also have tangent of theta, which is opposite side divided by adjacent side. So what if we want to find theta and we know opposite and adjacent? Well, that's pretty easy. We can use just that. Okay. We'll do this in our so inverse tangent times opposite over adjacent. Inverse tangent can be found if you use the second key on your calculator. Let me just look at it real quick. Second key on the calculator, and you hit tangent, you're going to get inverse tangent. Okay? So inverse tangent, inverse cosine of adjacent over hypotenuse gives you theta. Inverse sine of opposite over hypotenuse gives you theta. Inverse cosine gives you adjacent. Inverse cosine of adjacent over hypotenuse gives you theta, and then inverse tangent of opposite over adjacent. So those are ways to get theta, to get some angle. Alright, angular velocity is just some angle divided by some time. Okay? Now the most common one you're going to run into is RPM. So that's rotations per minute. Okay? We know a rotation is 2 pi radians. We know a rotation is 360 degrees. Just for reference, 0.1047 radians per second is 1 RPM. And 9.54 RPM is 1 radian per second. So you can do those conversions there if you need to. Alright, let's do a conversion real quick. We have 12.5 rotations per minute. We know there are 2 pi radians in 1 rotation. We know there is 1 minute is 60 seconds. So minutes cancel, rotations cancel, we get radians per second as our final unit. We do the math, we come up with 1.3 radians per second. Pretty simple, huh? What can we use to measure angular velocity? We can use a stroboscope. Stroboscope is pretty interesting. We're actually going to use one. There is some issues with stroboscopes you have to watch out for. You can use a tachometer, a laser tachometer. Usually a laser tachometer you have to have some sort of differing color. A lot of times we use a reflective strip. Or a contact tachometer, which has the advantage of just being able to be rested on whatever it is that's rotating. And the disadvantage of that is if it's whatever is rotating is it's rotating very fast, or it can be dangerous to do that. But if you can touch it with it, then that's the easiest way. Stroboscope is not too bad. Like I said, there is some disadvantages called aliasing that we have to watch out for. And a laser tachometer, if you have the reflective piece on it, is the absolute easiest. Sometimes you don't have to have the reflective piece, but it just depends. Angular acceleration is the same thing as our linear acceleration, is change in angular velocity divided by change in time. So we have a shaft on a motor rotating at 17 RPM. The power to power the motor. The power to the motor is increased, resulting in 8 RPM increase over 1.1 seconds. What is angular acceleration in radians per second? It should be second squared. Give me just a second. There we go. It seems that my pen has stopped functioning. There we go. Sorry about that. So we have angular acceleration, which we use alpha equals change in angular velocity divided by change in time. Change in time equals 1.1 seconds. Our change in angular velocity equals our final angular velocity minus initial angular velocity. I'm sorry, I was looking because it's actually given to us directly right here, but we're going to go ahead and do it the long way. So our initial angular velocity is just 17 RPM. Our final angular velocity is going to be 17 plus 8 RPM, which is equal to 25 RPM. Change in angular velocity is just going to be 25 minus 17 equals 8 RPM. We can then do a conversion to radians per second. So 8 rotations per second. I'm sorry, per minute. Times 2 pi radians per rotation. Rotation cancels. 1 minute, 60 seconds. Minutes cancel. We get 0.87. I'm sorry, 837 radians per second as our change in angular velocity. So all we have to do is 0.837 radians per second divided by 1.1 seconds. This also can be looked at as 0.837 radians per second times 1 over 1.1 seconds equals 0.76 radians per second squared. Alright. And that will be, we went to do a couple more problems. Converting angular velocity into linear velocity. A car tire has a diameter of 28 inches. How fast is the car going if the wheel has a angular velocity of 3.5 radians per second? Okay, there's a couple ways you can do this. You can go to radians per second and then just use the radius, or you can use circumference. I'm going to do both ways real quick. So our radius equals 28 divided by 2, which is going to give us 14, and that's in inches. So circumference what we're going to use is 2 we could say 2 pi times 14 inches equals 87.96 inches. Okay, so that's how far you're going to move for every rotation of the tire. If you have an angular velocity of 3.5 radians per second, we can do that conversion into rotations per second. So 3.5 radians per second, and we're going to do 1 rotation equals 2 pi radians. Radians cancel. We get 0.557 rotations per second. And then we get 87.96 inches per rotation. Rotations cancel. And we get 48.99 inches per second. I do know that's not the exact answer we're looking for. We will come back to that in a second. Let's look at another way to do it. So 3.5 radians per second. And we can times this by 14 inches per 1 radian. You can sub in your radius for radian. And then radians cancel. And you get 49 inches per second. So basically the same thing. So from there, this is probably the easiest way to do it, by the way. So all of that, or you can do everything up here above the line, or you can do everything below the line. Get the same answer. So the radians per second is a little easier, depending on what's given to you, but radians per second can be easier in a lot of cases. So all we have to do from here is do 1 foot, it's 12 inches, 1 yard, 3 feet, 1 mile, 1760 yards, 60 seconds, 1 minute, 1 minute, and 60 minutes is 1 hour. Minutes cancel, seconds cancel, yards cancel, feet cancel, inches cancel. We get miles per hour as our final answer. 2.78 miles per hour. And then we can do the other way around. So we can do convert angular acceleration into linear acceleration. I'm sorry. So this is acceleration of angular acceleration to linear acceleration. Car has an acceleration of 5 meters per second squared. What is the angular acceleration of the wheel if the car has a diameter of 78 centimeters in terms of radians per second? So our acceleration equals 5 meters, meters per second squared. We have a diameter of 78 centimeters, which equals 0.78 meters. The radius is therefore 0.39 meters. So it's really simple. We do 5 meters per second squared times this by 1 radian per 0.39 meters. Meters cancel, and we get 12.82 radians per second squared. Super simple. Of course, we could do there's much longer ways of doing that. So I believe that is it. If you have any questions, let me know.